now. And Rob, please get started. Thanks.
Cool. Yeah, thanks so much. And thanks for the opportunity to speak. I guess this is something that is kind of an interest that's developed really like as a hobby over a little while for me, that I guess is kind of motivated by some kind of annoyances or issues that I've noticed in the course of doing theory for different projects. And I guess I'm quite keen to sort of share with you all, because I think given we kind of approach problems theoretically we think sort of in a similar way when we approach problems, I'd be quite interested to hear if there's kind of concerns that other people share as well, and yeah, essentially what you all think. So yeah, I guess to sort of motivate this a little bit more, I'll start by just reading this quote. It should be said, for someone trained in formal methods, the area of probability theory can be rather sloppy. Everything is called P. Types are hardly ever used. Crucial ingredients like distributions in expected values are left implicit. Basic notions like conjugate prior are introduced only via examples. Calculation recipes and algorithms are regularly just given without explanation, goal, justification, etc. This hurts, especially because there is so much beautiful mathematical structure around. And this is by someone who's not actually a probability theorist or a statistician. It's by a computer scientist known as Bart Jacobs. And perhaps we might think that this is a little bit unfair, especially for someone kind of outside statistics, but perhaps as well, maybe all of us are kind of aware that some aspects of this are somewhat true, and maybe we'd kind of like to improve on them. And I guess to kind of dig into what is sort of causing this, or what kind of perhaps gives rise to this situation, we can kind of zoom in and look at like the sort of typical setup that we assume when we're doing classical probability theory. So the sort of classical story that we're taught is that we start with an underlying probability space, omega. I guess technically this is a set omega equipped with a sigma algebra, sigma of omega. And then we have this measure on the sigma algebra, big P. And we model the phenomena of interest that we care about using random variables. So these are measurable functions from omega to some space that respect the sigma algebra essentially in the appropriate way. And we can consider kind of many different random variables, so many different choices of x and y, but we sort of have this fixed underlying omega that's kind of hidden away in the background, and we have this big P that's sort of there also. And we're typically interested, even though we kind of start with this big P and we start with omega, we're actually typically interested in the joint or marginal behavior of x, y, etc., these random variables, rather than necessarily what's going on in this underlying probability space. And I guess like this picture is kind of complex. It's there's sort of many different components that are all playing seemingly different roles. So there's the underlying measurable space. There's this probability measure P, which is something else. It's a probability measure. It's not a measurable space. There are these random variables on top of the measurable space. And then from those, we pull out like the joint or marginal distributions of those random variables and often kind of study those. So many different components. And to some extent as well, this is also somewhat at odds with how we think intuitively. So, these joint and marginal distributions come like at the fourth step here, they're sort of secondary objects. They're not necessarily the first thing we write down. We write down kind of, technically this omega and P, and then we sort of extract these distributions kind of via a push forward. And that's somewhat at odds with basically how we think, say, in Bayesian statistics, where we're used to writing down a distribution as kind of like the first thing. It also, somewhat more subjectively, perhaps, random variables are kind of static. So you sort of can't sample from a random variable. They're sort of like a fixed quantity that has already been defined. They're just like a function on a measurable space. And, that's potentially a good thing, or it's an adequate way of modeling like a fixed data set. So you can model kind of the rows of your data set as random variables, for example, where you've got like this fixed kind of table to work with. But I think that's often ill-suited for describing computation. So, for example, if you are analyzing the output of an algorithm that depends on some randomness. You sort of have to like set up this probability space kind of implicitly where like all the random variables that will ever be like obtained from this algorithm are kind of jointly defined even before you kind of run the algorithm or anything. You sort of have this entire sequence of outputs that you have to define all at once. I guess additionally as well, conditioning in this picture is very technical. This is something we do all the time, obviously, and I guess if you kind of dig down to use sort of the general Kolmogorov definition of conditioning, it becomes really messy and sort of hard to work with, and often very removed from sort of our intuitions about what conditioning means. And I guess the sort of like underlying point of this talk is that basically working at this low level is kind of like using a very low level programming language that is sort of very complicated and hard to reason about at higher levels of abstraction, and makes hard to say things that potentially should be easy to say. And I guess the potentially what the conclusion of this is that an alternative way to do things would be to use categorical probability, which sort of reorganizes this theory in a way that allows reasoning about these higher level concepts in a more streamlined way. So it's not necessarily trying to create like a new theory. It's about sort of repackaging sort of the existing theory in a way that kind of scales better to these more complicated settings. And I guess it's one thing to sort of say this and maybe give some like high-level examples, but I think probably a more convincing way to do things is via a case study. So that's essentially how I've structured this talk today. It's based around this paper here, which was published in JMLR quite recently, in the last couple of years. And I actually think it's a really good paper. I think it's really well written. I really enjoyed it, but I think it does potentially exemplify some of the issues that arise when applying this sort of classical notion of probability, or this classical kind of way of doing probability theory, to sort of a modern context involving computation, sort of more complicated situations. And so the background to this paper, so often it's desirable to be able to parameterize a function so that it is invariant to the action of a group. So one example might be if you have data that consists of sequences of profiles of subjects in some sort of IRD population, and you have a group that consists of permutations of the indices of this sequence, or these sequences, and you have some function that is designed to make some prediction about the population. So it takes this entire sequence of information about the units and then produces a prediction sort of globally for that whole sequence. It's intuitive that in that context you would want that function to be invariant to permutations of the indices. And so the question, I guess, this paper is sort of motivated by is saying, like, okay, for a given group G, can we characterize the class of functions from some space to some other space such that they are invariant to the action of the group? Essentially all this is saying. Actually, the paper considers a slight generalization of this. They consider basically a probabilistic version. So they're basically saying, all right, let's model the input to our function and sort of the output as random variables x and y. And so we're implicitly allowing the function to involve some additional randomness so that y is like still random, even conditional on x. So x is the data and y is the prediction. And the goal of this paper is to characterize when the prediction is conditionally invariant with respect to the group in this sense here. So basically commuting the or applying the group action to the input space essentially doesn't affect the conditional distribution of the prediction. And this is kind of the main theorem of the paper. It's one of two theorems. So I guess I'm not talking about, they also have a result about equivariance. I'm talking about just the result about invariance here. So this is their kind of result about that. And basically it says the following. So it says, given these random variables representing your data and your prediction, if you've got Borel spaces X and Y, where these random variables take values, and if the group of interest is compact, and if the marginal of X is G invariant, and if we have a maximal invariant, I'll say what that is in a second, function defined on X, then the conditional distribution is G invariant in the sense that I just described if there is this measurable function F that basically gives you this kind of noise outsourced representation of the prediction. So it's basically saying the prediction here, Y, can be expressed as like a measurable function of the input mapped through this function M and some additional uniform noise that is independent of X. And so what is this function M? So a maximal invariant here is basically a measurable function that gives you the same value if and only if two points in the X space can be obtained by applying some element of the group to one or the other. So it's essentially saying, as I think many of you will be familiar, when you have a group action, you immediately get an equivalence relation defined on your on the space on which that group acts, basically defined by the orbits of that action or induced by that action. And so a maximal invariant is a function that takes a unique value on each orbit induced by that group. So essentially it's saying, given your data, you sort of attain this, like, you depend on just the orbit that you're in and also some randomness in order to obtain your prediction. That's basically the idea. And so you can think about kind of proving a result like this. And maybe you would do so if you're like me with some initial trepidation, because it seems, quite complicated. And the proof that they actually include in the paper is very complicated and uses all sorts of various technical notions like measurable cross-sections, normalized Haar measures, orbit laws, and conditional independence, which might not seem like a very technical notion, but I guess if you want to do this in the abstract kind of Kolmogorov definite sense of conditioning, then it is indeed very complicated and takes a lot of effort to actually do. In addition, I guess as you saw in the statement of the result, the statement of the theorem, that the result only applies when the group is compact and when X has a G invariant marginal, which is also kind of a bit weird because, like, why should the marginal distribution of X affect whether or not a neural net is invariant to permutations of X? In some sense, it's sort of like what's happening to X is sort of before it reaches the neural net. It shouldn't really affect whether or not the neural net itself is kind of invariant to the action of the group. But this is a condition that they require in this result. And so you can think about kind of like why this is hard, why is this actually hard to prove? And one thing to sort of think about with this is like, well, what would this be hard to show in the deterministic case? So if we were to go back and we were to basically pretend that Y is now a deterministic function of X. So this kind of no noise, this is sort of I guess you can think of this as like a special case. I'm being a bit hand-wavy here. In that case, essentially what this result is saying is that an output of a function is invariant with respect to permutations or actions of this group, if and only if that function is sort of mapped through basically this quotient space here. That's essentially what M is doing. And that's really just the definition of being invariant. And I'll make that precise in a more concrete way later in this talk. But essentially, it doesn't tell you really very much about how to like parameterize this function F or sort of what you need to do to actually define this F. It's just saying, just sort of another way of saying basically that F is invariant. It's a function defined on this quotient space. So in a sense, it sort of shouldn't be that hard potentially to prove, certainly in the deterministic case, and then conceivably not in the probabilistic case either. In addition, I guess you can also sort of think about, well, why are we modeling like a neural net in terms of random variables, right? Like we're sort of modeling the input and the output of this neural net, but we're not actually modeling the neural net itself. It's kind of gone, and we kind of extract the neural net almost like from the joint distribution. We have to sort of pull it out of this setup rather than having it kind of there directly to work with. We don't sort of a priori have like F, I guess, to begin with, which is also kind of a bit weird. And I suppose I mentioned this before, but it's also somewhat unintuitive that the distribution of X needs to be invariant to the action of the group if what we care about is defining a neural net in a particular way. And so basically what I'm going to show is that you can kind of approach this result from a categorical perspective and not only sort of generalize it, but also prove it in a way that maps directly onto our intuitions, potentially about how things ought to work. So here's a kind of brief aside and sort of a bit of background about categorical probability, I guess category theory more generally. So what is a category? Essentially, a category is a collection of objects and a collection of arrows. And I use the word collection advisedly because these need not be sets. They can be bigger than sets. So you can sort of consider the category of sets, which you can't have a set of sets if you're familiar with Russell's paradox, but you can kind of reason about this kind of at a higher level. Each arrow in this collection of arrows has a source and a target object. And we denote that sort of in a sort of standard way, like kind of as a function. And there is a notion of composition defined on arrows such that whenever you have appropriately typed arrows F and G, you can obtain a new arrow, G after F, that sort of has the corresponding typing in the same way as you would with kind of a standard function. And this composition operation is associative when again you have sort of the appropriately typed inputs. And the only other property that we need is basically the existence of identity arrows, which are defined basically, they're sort of assumed to exist. They are arrows going from an object to itself that basically compose in the way you would expect with all other arrows. And that's really it. So that is kind of the definition of a category. And overall, I suppose the philosophy of category theory is about sort of studying structural properties of the category extrinsically in terms of arrows in the category, not necessarily studying sort of kind of properties of individual objects at kind of the in a sort of analytical way, if that makes sense. I hope you get sort of a flavor of kind of how that works in this talk. It's kind of hard to convey at a high level, but that's basically the idea. You sort of don't want to look inside the objects themselves. You sort of want to study the objects by basically the arrows that go into an object and out of that object and how they relate to the rest of the category. So there are all sorts of categories in practice. So, classic example is the category of sets and functions. So the objects are sets, the arrows are functions. Another category that we'll talk about is the category MES, which is the category of measurable spaces and measurable functions. So you can check that this also satisfies the axioms of the category. On top of that, we can also think about a category called stock, which I'll actually define more explicitly later in the talk, which consists of the category where the objects basically of this category are again measurable spaces, but the arrows now are Markov kernels instead of measurable functions. And these are sort of quite big examples of categories, but there are other examples as well that are sort of smaller scale or sort of that look very different. And one such example is basically a group can be thought of as a category where there is a single object, the arrows of the group correspond, or the arrows of the category correspond to the elements of the group. You can compose them, and this category just happens to have the property that each arrow has an inverse, essentially. Okay, so the only other definition that we need is the definition of a functor. So essentially a functor is basically an arrow between categories in a particular sense. More precisely, if you have two categories, a functor between those categories assigns, it's an assignment that acts on both the objects of the first category and on the arrows of the category. So it's kind of overloaded. So big F here is our functor. It will apply both to X and also to little f. And essentially we just produce a new object, given an input object through this functor, and we also produce a new arrow for each arrow in the original category by applying this functor as well. Kind of a fairly natural thing to do. But moreover, I guess we need to assume that this functor sort of respects certain structure in the original category. So in particular, it preserves identity. It preserves the identity arrows in the original category in this way, and it also respects composition in this way as well. So quite a natural sort of definition. In the case, for example, of a, if we're thinking of a group as a category, you can show that, for example, a functor between groups corresponds to a homomorphism of groups, for instance. Okay, so I guess we're going to sort of focus more specifically on the setting relevant for probability now. One thing we often write down in probability theory or statistics is the set of probability measures on a given measurable space X. So I'm going to drop the sigma algebras for most of the rest of the talk because it's kind of cumbersome. Let's let Px denote this set of probability measures. It turns out that P, this thing that we kind of write down often without necessarily thinking about it, can be thought of as a functor on the category of measurable spaces and measurable functions. So what do I mean by that? Well, to be a functor, we have to, first of all, map each object in each measurable space, essentially, to another measurable space. So we need to equip Px with a sigma algebra because we've defined it only to be the set of probability measures. In order to be a measurable space, it needs a sigma algebra as well. So what's the sigma algebra that we can equip this set of probability measures with? Well, a very natural choice turns out to be the initial sigma algebra generated by these evaluation functions. So by that, I mean the smallest sigma algebra such that all of these functions eval that map Px to the interval 0, 1 become measurable. What does eval do? Eval is a function that takes a probability measure as input and then evaluates that probability measure at a fixed set A. We're going to consider sort of the collection of all of these across different measurable sets in our sigma algebra on X, and then we're going to choose the coarsest sigma algebra on P of X such that these are measurable. Okay, so we have now essentially an action. The functor is sort of defined on objects of the category MES. We need now a definition for what it does to the arrows in the category MES as well in order to be a functor, because remember that functors are sort of overloaded on both objects and arrows. And so given a measurable function from between measurable spaces X and Y, we need now a function, a measurable function between the measurable spaces P of X and P of Y. These are probability measures on X and probability measures on Y. And the natural thing to do here is to define that to be the push forward. So now we have, well, I guess I will assert that this turns out to satisfy the axioms of a functor. It's not hard to believe, but it does require a little bit of proof. But essentially, once you do that, you can sort of show that this is indeed a functor.
Hi, Rob. Just to check, what are the objects in MES again?
Measurable spaces.
Okay.
Yeah.
And so, what would the corresponding identity map be?
The identity functions, which are measurable.
Right. Okay. Okay. Thanks.
Yeah. Yeah. I guess. Yeah. I should have made that clear. Indeed. So great. So we have this category of measurable spaces, measurable functions. We have a functor from MES to MES that maps a set to the set of probability measures, or maps the measurable space to the set of probability measures on that measurable space, which we're now thinking of as a measurable space itself. Okay, great. So this is kind of already starting to reduce the complexity of our original picture, because now, like, a probability measure can kind of be thought of as as almost part of this universe in a way. It's like it's now an element in a measurable set rather than being some construction that we've sort of brought in on top of like this universe of measurable sets as well. Okay.
I have one more question.
Yeah.
So does MES depend on your state space, or is that for every state space do we have MES, or is MES for all possible state spaces?
Yeah, MES consists of all possible measurable spaces. like the objects consist of all choices of measurable space X. And we can zoom into particular ones, like you can choose your X of interest for your application and kind of focus on that. But yeah, I guess MES consists of sort of all of them. Like we're really zoomed out, I guess, at this point.
All right, awesome. Thank you.
Okay, so all right, so we have this P of Y, which is now like a measurable space of probability measures on a given measurable space Y. We can consider a measurable function going from X to P of Y now. Okay, so this is measurable space, so we can consider measurable functions that map into this. What does that mean? Well, by definition of P, if we fix a given input X in this measurable space here, this is just a measurable function, so we can kind of evaluate it at a given value X. And then we look at basically, like we're going to get a probability measure out. So, you know, we can kind of look at that as a function, like the output that we get from K is the function, it's a probability measure. Alternatively, we can also choose a given measurable subset of Y, and we can consider the function obtained by basically fixing that measurable subset and sort of considering all of the inputs that we could apply to X. And by construction of the sigma algebra that we put on P of Y, this thing here just rewrites to like evaluating K at B. That's basically the definition of these eval functions. By definition of the sigma algebra we put on this, which is initial with respect to these eval functions, this thing is measurable for any choice of B. So in other words, A is a Markov kernel. So, you know, a function from X to this P of Y is basically the same thing as sort of what we're familiar with as, you know, we typically write a Markov kernel, I guess, as like a function that takes as input both a value in X and also a measurable subset of Y, and then produces a probability. But you can sort of consider this basically the same thing. I mean, the only difference is basically where we put the brackets. Do we put them there, or do we put them like, yeah, do we put a comma there instead? More precisely, if you want to kind of draw a correspondence between these two, we could think of like this function going, this measurable function from K to P of Y as a measurable function going from X to P of Y as a measurable function that takes X as input and then returns a function which takes a measurable subset and gives you a probability. This is the set of functions from, you know, sigma Y to 0, 1. Basically, this thing here is a curried version of this sort of function signature that we're used to. It doesn't really matter if that doesn't make sense, but you can hopefully see the analogy. The only real difference is kind of like a formal one is basically, are we putting brackets or are we putting a comma? Okay, so great. So we can consider Markov kernels to be generalized measurable functions. In particular, every kind of normal measurable function f from X to Y can be canonically identified with this function going from X to P of Y, which basically lifts f to essentially output Dirac mass on its output. So it kind of, this delta function here is going to take as input some Y and just return a Dirac measure on Y. So essentially what we're doing here is, you know, f would normally just output a value of Y. Delta composed with f takes that value of Y and just gives you a Dirac mass associated with that. And this now has a signature going from X to P of Y. And we said that functions going from X to P of something are Markov kernels. So this is now a Markov kernel. Okay, so we've now kind of generalized like this kind of standard like functions, the measurable functions. Can we do this again? Could we consider generalized functions? So could we consider functions going from X to P of Y? And in a sense, we sort of can't, because basically when you go up this additional level of abstraction, you can kind of canonically identify the result with this function that basically maps essentially just to one layer up. So instead of going from X to P of Y, we can consider this as a function that just goes from X to P of Y. And basically what we're doing here is we're composing that sort of generalized function with this this function E, which basically just averages out essentially what's going on here. PP of y is essentially probability measures on y. Okay, so what we're doing here is we're taking a probability measure on probability measures on y, and we are kind of getting a probability measure just on y by averaging out essentially all of the choices of Q. Another way to look at this is like, given that the output here is P of y, we can consider this thing to be a Markov kernel. Okay, so it's a Markov kernel that takes a probability measure on probability measures on y. What does it do? First of all, samples a probability measure on y from the input that it's given. And then it samples again. And it's essentially just a two-step kind of Markov kernel that gives you kind of a standard Markov kernel back. And I'm kind of aligning some details here. Basically, it turns out as well that these deltas and e's also satisfy some coherence condition that give rise to something called a monad on MES. It's a term that I think many of you will be familiar with, particularly, I guess, if you like functional programming. Essentially, it's kind of a general like concept that appears in category theory that this is kind of just one instance of. And so you get sort of a whole lot of nice results for free. But we don't need to necessarily worry about that too much this talk.
So the second example you gave here is reminiscent. I forgot the exact term now. Like in functional analysis, where you have a Banach space which is isomorphic to its second dual, right? Is it basically the same thing that's going on here? Because we're working with probability measures, it's basically always of that type. I've literally forgotten the technical term. You know what I'm talking about?
Yeah, the double dual. Yeah, you very well might be right. So what I know, there is a result which says like the double dual, like an example of that is like sorry, that constitutes an example of a natural isomorphism of like, anyway, there is a notion of like natural isomorphism between functors in category theory that's sort of like better than just like a sort of isomorphism. I guess category theorists use that as an example that distinguishes like, because I guess the single dual is not naturally isomorphic to the dual, but the double dual is.
Yeah.
That result that I'm thinking of is different to this, but very well you might be right that there is a way to interpret that in this setting as well. I have to think about it. I haven't thought about it.
Okay, thanks.
But yeah, it's a very categorical notion that you point out. Okay. So, all right, so we have this monad on MES. Basically, it turns out that in general, monads give rise to a sort of canonical notion of composition of like generalized arrows, or in our case, generalized measurable functions or Markov kernels. And so how does this work? So let's say we have two Markov kernels now, K going from X to P of Y, and another Markov kernel going from Y to P of Z. So we wanted to find a notion of composition of these. We can't just directly compose these in the category MES because this thing here has an output that takes values in P of Y, whereas the input here requires a Y. It doesn't take a P of Y. So this won't like directly compose. But because we have this monad structure, we can define a notion of composition in a sort of canonical way. This applies to all monads, but we're going to instantiate it, I guess, for this monad that we've defined above. And basically the way you do it is you first of all consider your arrow X to P of Y, it's K arrow here. And then we apply the functor P to this L here, which gives us now an arrow in MES going from P of Y to PP of Z. Essentially, we just put P on both sides of this. It's a functor, so that's essentially the signature that we get. And then we have this sort of additional step where we kind of go back down a level by applying this E that we defined above. So this now gives us, given a K and given an L, we get basically this new arrow that goes from X to P of Z. It essentially looks like something that you could call a composition, essentially of this form here. You can actually show that essentially that does constitute a valid definition of composition. And actually you can show that in the case of MES, this reduces to the Chapman-Kolmogorov equation. It's kind of what you would expect, composition of Markov kernels. But it's quite nice that just pops out for free in this canonical way, and actually lets you avoid having to prove the Chapman-Kolmogorov equation. Once you've proven that P is a functor, and once you prove that in general you can obtain composition of generalized arrows in this way as well, you get this for free. It's not an easy result necessarily to prove by itself, but it does pop out naturally from this theory, which is quite nice. And I guess in addition, this notion of composition that we've defined, we also obtain identity kernels, I guess, or identity Markov kernels corresponding to these Dirac maps. You can sort of check that when you plug this in and you compose this Dirac map according to this definition, you get sort of what you started with, which makes sense, and I guess will be familiar. Will be familiar to I guess most of you, given your backgrounds in CMC theory. Cool. Okay, so that notion of composition that I just defined is called Kleisli composition, and it gives rise to something called the Kleisli category. This is the notion, as I said, that applies sort of anytime you have a monad. But in the particular case of MES, we get a category we'll call stock, which corresponds to the Kleisli category of MES obtained in this way. And so just to kind of summarize what's going on here, so in MES, we said the objects were measurable spaces, the arrows were measurable functions, composition was just composition of measurable functions, and identities were just identity functions in MES. In stock, what we get instead through this construction is the objects still are measurable spaces. The arrows now are Markov kernels. Composition corresponds to the Chapman-Kolmogorov equation, and the identities correspond to these Dirac maps that we defined. All right, so we have actually a bijective correspondence between measurable functions and Markov kernels. Measurable functions of this signature going from x to p of y, and Markov kernels going from x to y. This is actually a special kind of bijective correspondence. It's actually another example of a natural bijection as opposed to just like a bijection. The name for this is an adjunction. It doesn't really matter for this talk, but it's kind of a canonical thing that you always get anytime you use this Kleisli construction. So we saw before that identity kernels correspond to these Dirac maps via this bijective correspondence. An interesting question to consider is what Markov kernel corresponds to the function ID py, right? So this is a Markov kernel. This is a measurable, we're going to view this side as this is a measurable function, right? So it's the identity function on the set of probability measures on y. It has output taking values in p of y. So we can actually consider this to be a Markov kernel that takes a probability measure on y and gives you a random element in y. That's, and anytime we have p of y here, we said we could view that as a Markov kernel. So we can do that in particular for x equals p of y. So what is the Markov kernel that actually corresponds to this measurable function? It's not the identity, because that would correspond to the Dirac map. It's something else. What is it? It's actually this function called samp, which basically takes a probability measure as input and draws a sample from that as its output. It's a Markov kernel that does the sampling operation. We sort of write this down in a kind of like, I guess all the time. We write this tilde operator all the time, and we sort of view that almost something outside of our measure theory, etc. But actually, it corresponds to composition with a particular arrow in this category of measurable spaces and Markov kernels, which I think is kind of cool. That's basically the idea. And yeah, so basically, I guess the picture we have overall is of stock now sort of looks like this, where we previously had random variables defined on a probability space. We can sort of replace those random variables with these kind of lifted versions where we sort of, here we have the measurable function composed with this Dirac map that lifts x to be a Markov kernel that just happens to be deterministic. We can view the original probability measure big P as a Markov kernel defined on a space that has just a singleton element in there. So it's a Markov kernel that just has one input. It's the same thing as a probability measure, essentially. And then this composition here would correspond to like the push forward of x under, or push forward of P under x. And as I say, we can also view sampling in this picture as like literally composition with a particular arrow here. Essentially what this guy is doing is saying, take your kernel, take some sort of arbitrary kernel K, and instead of like returning a random element, in this case in Z, you can sort of imagine returning like a frozen probability distribution on Z. corresponding to the distribution of K. That's what this delta of PZ is doing. And then samp here is just saying, okay, now I've got this frozen distribution to sample from, and that's the same thing as the sampling from K directly. This is, yeah, and I guess as well, you know, we have this picture. We actually don't really need this anymore to some extent, but you could use this if you wanted to. All right, so I'm just very aware of time. So we have these two categories of interest: measurable spaces and measurable functions. We have stock, which consists of measurable spaces and Markov kernels. We have this functor that maps a measurable space to the space that probability measures defined on that, on the original space, I guess. And we obtain stock in this kind of canonical way via this Kleisli construction. Alternatively, you could also just show directly that stock is a category. That's possible to do as well, and it's totally fine for the purpose of this talk. But you can kind of, I guess it's nice to sort of see that that it falls out in this kind of canonical way. Okay, so returning to the case study, this is the result we had. We said X and Y are random elements, and we have this compact group acting on X, and we want to basically obtain this sort of noise outsourced version of Y, where instead of, we basically obtained Y by mapping X through some M, and then adding some noise through this function F. So we're going to basically consider, we're going to sort of take the same sort of like philosophy of category theory and sort of emphasize sort of structural properties that exist for this category and apply these in our particular case that is sort of assumed in the statement of that theorem. So one structural property that is very useful that the category stock has is that if you've got a standard Borel choice of Y, then any distribution on the joint space can be disintegrated in this way. I think this is a familiar result, but you know, it's something that we can show holds always for any choice of Borel Y. And it's useful to have basically a graphical way to denote this. So you can do this in a couple of different ways. One way, and I guess category theorists do this a lot, is they use commutative diagrams. So you know, this diagram here on the left is basically saying, so a commutative diagram is essentially saying that all paths that start and end at the same point are equal, or all compositions of arrows along paths that start and end at the same point are equal. So this diagram on the left is saying that, you know, if we think of P as a Markov kernel that takes a singleton set as input and just returns essentially a sample in the joint space, that is the same thing as sort of, you know, returning your sample in the joint space, projecting down to just X, copying that output to X by X, and also then applying K to one of these inputs. You know, not so this identity arrow here, or this part of this arrow here, allows essentially the X input to just apply, like it just sort of flows through unaltered. And then we apply K to like this other X input here and get sort of an element in Y. That's basically what this tensor notation here means. And so this commutative diagram is expressing this statement up here in integral form. Alternatively, we can write that as a string diagram, where basically we have this joint distribution on the left. We basically, so you read this from the bottom to the top. So this is expressing an arrow going from the singleton set to the product space X and Y. That is the same thing as sort of an arrow that starts at the singleton set, discards its Y output, takes its X output and copies it through. One component goes just directly through to X. So it's the same thing as just sampling from the X marginal of P here. The other component here goes into this other box A, which you then sample and output given that input as well. So this here is basically just a way of denoting the same condition here. Okay, so you can always kind of choose a K such that this condition holds in the case of stock, provided Y is standard Borel. Okay, so we're going to define just another notion here as well. So, suppose we have an arbitrary equivalence relation on our measurable space X. Previously we were looking at invariance with respect to a group action, but it's sort of more convenient basically just to kind of ignore the group and just look at the equivalence relation that it introduces. And essentially the natural thing to do in that setting is to define conditional tilde invariance in this sense here. So we're going to say that a joint distribution on X and Y is invariant with respect to tilde if there is a disintegration in this sense defined here that is marginally invariant with respect to tilde. So essentially the Markov kernel K has the same output distribution whenever the two inputs are equivalent. So a natural thing you could write down. It turns out actually to be equivalent to conditional invariance in the sense of the paper under the assumptions that they assume. So when the group is compact, the marginal is G invariant, the output is standard Borel, and where the equivalence relation is defined with respect to the orbits obtained from that group. But it kind of makes sense more generally, and it's sort of something you would sort of naturally write down as a notion of invariance with respect to an equivalence relation, I guess, more even if there's not necessarily a group immediately involved. Okay, cool. So one other structural property that you can assume for that turns out to be present in the category of measurable spaces and Markov kernels is the following. So anytime you have a measurable space X and an equivalence relation on X, regardless of how complicated or however that's defined, you can always form the quotient space of X under that equivalence relation. So the way you do that, you need the sets here are the equivalence classes. Sorry, the elements of this set here are the equivalence classes corresponding to tilde. You need a sigma algebra as well to make this a measurable space, but you can do so in a canonical way by using the final sigma algebra defined with respect to the quotient map. So the quotient map takes an input X and outputs the equivalence class that X is a member of. We choose the sigma algebra here to be the finest sigma algebra such that this Q is measurable. Explicitly, it has this form here. So you basically look at all the subsets of the quotient space, and you check which ones lie in, or the pullback of those lie in the sigma algebra on X. It's clear that this is sort of the largest that you can define. Okay. Now, it turns out that a function G, a measurable function G, is invariant with respect to an equivalence relation if and only if there exists a measurable function G tilde such that this commutative diagram holds. So basically, if and only if G factors through this quotient map in this way. This is kind of you can prove this. You can do so with elementary definitions. It's something you do have to show. But it turns out to be a very natural result in the context of category theory. So this is expressing what category theorists call the universal property of the quotient. So it's essentially establishing a bijection between maps out of the quotient space and tilde invariant maps from X to Z. These correspond bijectively to these guys. So in a sense, you can sort of think of them as the same thing. That's made more precise by the fact that this is actually a natural bijection rather than just a bijection. But anyway, this is true and can be shown through relatively elementary means. Given that result, okay, we can take Z now to be, in particular, the space of probability measures on Y. Okay, so this applies to all measurable spaces Z. Let's apply, in particular, this result for this set of probability measures on Y. That's a measurable space that we've defined. Essentially, what that shows is that once we kind of interpret this result in stock, that we obtain basically this characterization of a tilde invariant Markov kernel. So a Markov kernel is tilde invariant if and only if it factors through this quotient map as well. This Q is going to basically play the role of M in the original statement of the theorem. Okay, great. That's one result. I guess to be clear, we're sort of identifying this quotient map. That was a measurable function previously. We're now sort of identifying that with kind of like a lifted version, sort of a deterministic Markov kernel, but it all works out. It's fine. All right, that's one result we need. The only other result, and yeah, thank you for bearing with me as well, is this one here. Basically, anytime you have a Markov kernel whose output space is standard Borel, you can sort of express that Markov kernel in this fashion here. So basically, it can be written basically in this sort of noise outsourced form where there's this measurable function f that you apply the input to f and you sort of apply some, this is uniform 0, 1, you can apply some noise to f as well and you get the same Markov kernel as you started with. It's kind of a natural thing that you would expect, and it's a standard result. Basically, it's the inverse CDF trick. So you can always do this. It's another kind of structural property that MES or stock, I guess, really has. All right, so here's basically the proof of the result now. So we're going to prove this. So if y is standard Borel, then the joint distribution of these two random variables, this is like the input to our neural net, this is like the output, the prediction. This is conditionally invariant with respect to an equivalence relation now, if and only if there is a measurable function such that basically this representation holds. So we've got this eta that's independent of x and it's uniform 0, 1, and it's expressed in this way. Here's the proof. Okay, so conditional tilde invariance means that basically these conditions hold. So we can always disintegrate P. We said we can start out with a joint distribution. We can always disintegrate it in some way like this. Conditional tilde invariance implies that basically we can actually choose this K in such a way that it factors through Q. That was basically this result back here. Okay, and then we have this K tilde, which outputs values in Y, and we know that we can always write a Markov kernel that outputs values in a Borel space Y like this. So we just apply that basically to this K tilde. So having set everything up, it follows very naturally. And I guess this is sort of proving one direction. This is proving that conditional tilde invariance implies basically this equation. If this equation holds, well, that implies tilde invariance because this part of the diagram is also you can show is tilde invariant basically because Q is the quotient map. Anyway, great. So I'm going to skip over this. It turns out that's not quite enough because we've shown equality in distribution, but that doesn't imply equality in almost sure sense, which is what is assumed in this or what's claimed in this result. It turns out you can basically do the same ideas here. So you apply sort of a noise outsourced construction, you get sort of an H that lets you rewrite basically this Markov kernel on the right-hand side. And a few more diagrams later, you get something that looks like this. I'll leave the slides up. You can see this in the recording if that's something that interests you. But yeah, essentially, having set up the structural properties of this category, the main steps of this proof are essentially just a matter of manipulating diagrams. And so here's the kind of final result that we get. Essentially, if the output is Borel, we've got conditional tilde invariance if and only if we get this almost sure expression of the random variables on the left-hand side. So we've replaced the distributional equality, which is what I just showed you with almost sure equality as well. Yeah, there's a technical caveat, but it's fine. Great. So yeah, I mean, that's kind of the end. I will basically stop there. Yeah, possibly, yeah, maybe I should just stop there and there's questions in the last couple of minutes. I'm happy to take those as well.